Hello everyone. Today we are going to look at algebraic vectors in R2. So that corresponds to 6.6 in your textbook. So let's start with the difference between algebraic vectors and geometric vectors. Geometric vectors that are considered without vectors that are considered without reference to coordinate system or coordinate axis, and algebraic vectors that are considered with reference to coordinate system. Let's give an example here. Geometric vectors. So one example would be, let's say 50 kilometers per hour. And then we can give direction as north 40 degree east, let's say. Algebraic vectors. So we represent the algebraic vectors with the coordinates. If we are in R2, we may have a vector OP. So in R2, we have two coordinates. So let's say 2 and 3. Or in R3, so a vector OP should be represented with three coordinates. Let's say 5, 0, 1. So let's define the algebraic vectors in R2. Any vectors may be translated to position vectors on the coordinate system. So position vector, let's remember, is a vector so that its tail is at origin and then head can be anywhere. So suppose P is a point with coordinates AB. So we have a point AB. So we can construct a vector with its tail at origin 0, 0 to point P, AB. So now this is the origin. So you draw a vector, tail is at origin, and then head is at point P. So then this vector is OP vector, and it's called position vector again. So, and that position vector is represented with the same coordinates as point P, so AB. And A is called the x component, and B is called the y component of the vector. Ordered pair versus unit vector notation. We can represent algebraic vectors two different ways. One is ordered pair. Let's say we may have a vector u, coordinates of it is a and b. Let's say that is 2 and 3. And we can also represent the same vector using vector notation. So that would be ai vector plus bj. I vector is a unit vector that has same direction as x-axis, and j vector is the unit vector that has same direction as y-axis. Okay, so if we use the same 2 and 3 coordinates here, then we can represent the same vector u as 2i vector plus 3j vector. Okay, so that is the I vector. You multiply that by a, so you get this vector, a times I vector, and then this is the j vector. You multiply by b, and you get bj vector. So then you add a times I vector plus b times j vector. As you see, you get OP vector. So how can we calculate the magnitude of that position vector? So you can use just simply Pythagoras, and this side is a, this side is b. So square root of a square plus b square will give you the magnitude of OP vector. Unit vector, so we looked at this concept before. Unit vector u has magnitude of 1 and is defined by, so u hat, u vector divided by magnitude of u vector. So if you have, again, if we have algebraic vector, if we have algebraic vector AB, So we take AB vector and divide it by the magnitude of AB. It's the magnitude of that vector that is represented by AB. So let's say again, if we use 2 and 3, then you take to find the unit vector. So we have vector 2, 3. So we divide it by the magnitude of that vector. The magnitude would be 2 square plus 3 square, so 9 plus 4 root 13. So that would give you then 2 over root 13 and 3 over root 13. And of course, you could rationalize the denominator here, and that would give you 2 root 13 over 13, 3 root 13 over 13, would be the unit vector that has same direction as vector 2, 3. How do we define I vector and j vector? So we define I vector as 1 and 0. Again, if we have xy system here, that I vector that has same direction as x, I vector, and coordinates of this point, as you see, 1 and 0. And j vector can be represented as 0 and 1. So j vector again has same direction as y. So that is j vector. So the coordinates of this point is 0 and 1. So to be vectors that point in the direction of the positive x-axis and y-axis, every vector in R2 given in terms of its components can be written uniquely in terms of I vector and j vector. So I and j are called standard basis vectors in R2. So let's look at some examples. So example 1, express each vector as ordered pair or unit vector notation. So the first one is given to you as ordered pair. So we're going to write this now as a unit vector notation. So we say that this is the x coordinate 5i plus negative 6j, so minus 6j. Again, this is given in ordered pair, so we're going to write it with unit vector notation. So 0i plus 3j, so that gives you 3j only. So C, that is given in unit vector notation, so you're going to put it in ordered pair notation. 6 is the x coordinate, negative 8 is the y coordinate. If you have 5j, so as you see, we don't see any I, so it means that x coordinate is 0 and y coordinate is 5. So adding two vectors in R2, to add of two algebraic vectors, add their component, corresponding x component and y component. Let's say we have OA vector and OD vector. So coordinates of A is A and B, coordinates of D, point D is C and D. Okay, so how can you represent OC? So OA plus OD is giving you OC vector, as you see. So we add the x coordinates, so A plus C, and we add the y coordinate, B plus D. Okay, so let's give a simple example. Let's say point A, coordinates of point A is 2 and 3. So OA vector is also represented by 2 and 3. So let's say point D is 5 and 1. So OD vector is also 5 and 1. So we want to represent OC vector, which is now addition of those two vectors. They are tail to tail if you use parallelogram method. So OC is OA plus OD. OA plus OD. So 2 and 3 plus 5 and 1. So that gives you 2 plus 5 is 7. 3 plus 1 is 4. So then C is 7 and 4 here. So that is additional two vectors. Now let's look at subtracting two vectors in R2. To subtract two vectors, we subtract their x and y components. Okay, so let's say we have, so we are looking for OE vector. So let's say we have OA vector again and OD vector. So when you subtract OD from OA, how would you draw the vector? You start from the head of the negative vector and go to the head of the positive vector, right? So you see a negative sign in front of OD. So you start from there and you go to the positive. So OA has a positive sign in front of it, so you go there. So that is a subtraction vector here. However, when you do the subtraction, you get a vector that is equivalent to this vector, but in as position vector. Okay, so if you take this AD vector or DA vector and move it so that the tail of DA is at origin, so that is OE vector. So when you do the subtraction, you get an equivalent vector that is a position vector. Okay, let's give an example. Let's say again, point A is 2 and 3, and point D is 5 and 1. So we want to look at OE vector, which is OA minus OD vector, if you look at this. And then OA vector is 2 and 3, and OD vector is 5 and 1. So you get negative 3 and 2. Okay, so as you see, so this is a position vector. This point, if you think it as a point, it is the head of the position vector where the tail is at origin. So this is then negative 3 and 2 in this case. Scalar multiplication in R2. Let's say we have k times OP vector. Okay, so coordinates of OP, let's say A and B. Then you can multiply each coordinates by that k, which is constant, to get that vector. Let's give an example. 5 times 2, 3 vector gives you 5 times 2, 10, 5 times 3, 15. Let's look at another example, example 2. So we are given U vector, coordinates 2 and negative 3, and V vector, 6 and 1. So we're going to find negative 6 V vector. Negative 6 times V vector is 6 and 1. So that gives you negative 36 and negative 6. Now we're going to find 2U plus 5V. So 2 times U vector plus 5 times V vector. That gives you 4, negative 6, plus 30, and 5. And finally, you add the x coordinates to add these two vectors. You get 34, you add these two, and negative 1. So U minus V vector, 2 and negative 3 minus 6 and 1. So 2 minus, we subtract the x coordinates now. 2 minus 6, negative 4. Now subtract the y coordinates. Negative 3 minus 1, negative 4. Algebraic vectors between 2 points in R2. Let's say we have point A, coordinates x1, y1, and we have point B, coordinates x2, y2. then the vector AB, so vector drawn from A towards B, can be found as x2 minus x1, so you subtract the x coordinates, and y2 minus y1, you subtract the y coordinates. So as you see, you take the coordinate of the second point and then subtract the x coordinate of the first point from that. Okay, so x2 minus x1, and same thing with the y coordinate. And of course, magnitude of it using the Pythagoras, the x coordinate of AB is x2 minus x1. You take the square of that. Y coordinate of AB is y2 minus y1. You take the square of that. You add them, and you take the square root of it. Let's give a numerical example here. Let's say point A, coordinates of point A is -3 and 2. So OA vector is -3 and 2 as well. Let's say point B is 5 and 4. So OB vector is also 5 and 4. So then if we want to get AB vector here, let me do it here. You want to get AB vector, so you take B vector and subtract OB vector and subtract OA vector from that. So 5 and 4 minus -3 and 2. So that gives you 5, negative, positive. So 5 plus 3, 8. 4 minus 2 is 2. So as you see, you get AB vector as a position vector. Okay, so you take that AB, move it so that the tail is at origin. Okay, so the vector that you get is that position vector. So 8 and 2. Of course, to calculate the magnitude of that OP vector, which is a subtraction of OP minus OA. Okay, so we can do OP, magnitude of it, square root of 8 square plus 2 square. So 64 plus 4, 68, and 2 root 20. Yeah, so you can calculate this, right? 68 can be divided by 4, so 17. So that gives you 2 root 17. Okay, so let's look at the examples. Given the points P and Q and R, find QP. So to get QP vector, we take P vector and subtract OP vector, and subtract OQ vector from that. OQ. So -6 and 1 minus -2 and -1. So -6 minus plus, so +2, so -6 plus 2, -4. 1 minus -1, 1 plus 1, which is 2. So we're going to find now for part B, magnitude of PR. So let's get vector PR. So we do OR minus OP. OR is -3 and 4. OP is -6 and 1. So -3 minus -6, 3. 4 minus 1 is also 3. So to find magnitude of PR vector, you use Pythagoras theorem. So 3 square plus 3 square, 9 plus 9, 18. That gives you 3 root 2. Let's look at example 4. Parallelogram OPQR is determined by the vectors OP and OR. Determine OQ, PQ, and PR vectors. Okay, so let's represent this. It doesn't have to be, you don't have to use a coordinate system. You can draw any parallelogram. So I'm going to take this as origin. So the coordinates are 0, 0. Now we have OP, so it is this parallelogram determined by OP vector and OR vector. So let's say this is point P, so that this vector is OP vector, and negative 3 and 2. And other one that determines this parallelogram is OR vector. This point is R, negative 5 and negative 3. So if this is OPQR, OPQR parallelogram, then I can name this vertex as Q point. Now what I need OQ. As you see, we can find OQ by adding OR and OP. If this OR and OP are tail to tail here, so you can use the parallelogram method, and this diagonal gives you, how can you get this diagonal? By adding OR and OP vector. So OR is negative 5 and negative 3. OP is negative 3 and 2. That gives us negative 8 and negative 1. So let's look at PQ vector. PQ vector, as you see, this is a parallelogram. So PQ is same as OR vector. But you could still prove that by doing OQ minus OP. OQ is negative 8 and negative 1. And OP is negative 3 and 2. So that gives you negative 3 minus negative 8 minus negative 3, negative 5. Negative 1 minus 2, negative 3. So as you see, PQ vector is same as OR vector, okay, because they have the same size and same direction. And when you do this subtraction, remember, you get a vector that is a position vector. So you get that vector as its tail is at origin. Okay, so next one is PR vector. So how can you find that? As you see, if you do OR minus OP, you can get PR vector, OR minus OP. OR vector is negative 5 and negative 3. OP is negative 3 and 2. So negative 5 minus negative 3, negative 2. Negative 3 minus 2, negative 5. And of course, you get that vector as its tail is at origin. You get it as a position vector. So when you get PR vector, actually you get this one that is equivalent to PR, so that the tail of it is at origin. And this point would be negative 2 and negative 5. Let's look at example 5. Find the components of the unit vector in the direction opposite to PQ, where OP 9 and 7 and OQ vector, OQ is 2 and negative 21. Okay, so PQ vector would be OQ minus OP, so 2 and negative 21 minus 9 and 7. So 2 minus 9 gives you minus 7. Negative 21 minus 7 gives you negative 28. So that is PQ vector. Again, you get it as a position vector. The tail is at origin, and the head is at negative 7 and negative 28. So we are going to find the unit vector not in the direction of PQ, but opposite to PQ. So the vector that is opposite to PQ is QP vector. So to get that, you just multiply PQ vector by a negative sign, -1. So that gives you 7 and 28. So we want to get a unit vector that has same direction as this. So we do QP vector divided by magnitude of QP. So let's calculate magnitude of QP. The square root of 7 square plus 28 square. So if we do that, we get 833. So square root of 833 is the magnitude of QP vector. So unit vector is then 7 and 28 divided by square root of 833. So then what would be the coordinates of U? 7 over square root of 833, 28 over square root of 833. If we rationalize the denominator, 7 square root of 833 over 833, 28 square root of 833 over 833.